Welcome to this explainer where we take insanely complex technical architectures and break them down so you can actually understand how they work under the hood. So picture this. You're standing outside, it's pouring rain, you pull out your phone, tap confirm ride, and literally within 3 seconds, a driver is locked in and on their way to you. I mean, it feels like absolute magic, right? Well, it's not. Behind that slick little loading screen hides a massive, high-stakes, real-time distributed system. And today, we're completely peeling back the interface to show you exactly how Uber's dispatch engine pulls this off.
To really grasp why building this system is such a monumental headache, you kind of have to wrap your head around the sheer scale of it first. 5 million. That is the number of active drivers globally on the platform at any given time. And the crazy part, these aren't just static data points sitting neatly in some database table. Every single one of these 5 million drivers is a moving target, constantly broadcasting their exact GPS coordinates over the network.
Which brings us to this absolutely terrifying number, 2.5 million. That's the peak volume of location updates, or database writes, slamming into Uber's servers every single second during a rush hour. Now, a standard relational database, it would absolutely melt down under 2.5 million updates a second. But the system has to process every single one of those pings. Why? Because if a location is even a few seconds stale, you get a totally wrong ETA and a completely botched match.
Okay, so here's the ticking clock that governs everything. The system operates on a ruthless latency budget of about 10 seconds. Think about it. When you request that ride, the architecture is exactly that long to ingest millions of live locations, find the absolute perfect driver, send them an offer, wait for their actual human reaction to tap accept, and confirm it all back to your phone. If that match isn't locked in within 10 seconds, riders get impatient, they cancel, and the entire system fails. Every microsecond matters.
All right, moving on to Section 1, shrinking the search space. So how on earth do you search through millions of moving targets in just milliseconds without instantly crashing your backend? Well, the very first major hurdle is figuring out how to radically shrink down that search area. You obviously can't scan the entire planet, or honestly, even a whole city, every single time someone needs a ride home.
If you tried a naive, greedy match, calculating the distance to every single active driver right that second, the database would just crash under the weight of millions of math operations. It's too much. Instead, Uber built a dispatch optimization engine, affectionately known as Disco. And Disco does something incredibly smart called batch matching. Rather than finding a driver the millisecond you hit the button, it bundles a bunch of requests over a 2 to 5 second window, and then looks up drivers in highly specific mathematical buckets.
Okay, let's dive into this because to make these lookups ridiculously fast, they use Google's S2 geometry library. It is super cool. Imagine taking the spherical Earth and projecting it onto a giant, flat 3D cube. Then you divide that cube into a grid of tiny, tiny cells. Using this brilliant mathematical trick called a Hilbert curve, it essentially folds the map up so that locations physically close to each other in the real world share similar numerical ID numbers. So, instead of forcing the server to do intense, complex 2D geographical math to find your car, the backend just asks a very simple database question. Hey, which driver IDs are currently sitting in cell ID X, Y, and Z? Now, because this data is moving at lightning speed, the live location index has to live entirely in memory. They keep it completely separated from their durable, slower relational databases. By using an in-memory store like Redis, they can actually survive that fire hose of millions of writes per second. When a driver drives across one of those S2 cell boundaries, their ID just pops into a new bucket. It's a lightning-fast O of 1 lookup, meaning it takes constant time, literally instantly. They are deliberately sacrificing long-term data durability here, strictly for raw, unadulterated speed. But they don't stop there with the optimizations. This part is actually brilliant. The system adapts how often it asks for a GPS ping based on exactly what the driver is doing right now. If a driver is idle, just hanging out waiting for a ride, their phone only pings the server every 5 seconds. I mean, why waste server power, right? But the second they flip to reserved and are actively driving to pick you up, it drops to 2 seconds. And if they are on trip with you, literally in the back seat, it updates every single second so that little car animation on your map is perfectly smooth. This adaptive pinging saves a massive amount of server overhead, actually reducing write capacity waste by up to 70%.
Let's move to Section 2, the concurrency trap. Because here is where the tension really cranks up. Even with all that incredible speed and batch matching, you still have millions of people using the app at the exact same time. So what happens when 2 riders standing on the exact same city block request a ride at the exact same millisecond? Well, if you're not careful, the system could easily promise the exact same nearby driver to both of those riders. Welcome to the concurrency trap.
In the software engineering world, this is known as the classic check-then-act concurrency bug, and it's a total nightmare for distributed systems. It happens when your system checks if a resource is available, like, say, an Uber driver, and then acts on it by assigning that driver to a writer. But in the microscopic split second between checking and acting, the state of the system fundamentally changed because another server already snuck in and grabbed that driver.
Let's walk through this panic-inducing timeline really quick. Millisecond 1. Writer A requests a ride. The server checks the S2 cell, sees driver Dave is available. Great! Millisecond 2. Writer B requests a ride. A totally different server checks that exact same cell, and it also sees driver Dave is available. Millisecond 3. Both servers act, assigning Dave to two completely different people. From the user's perspective, both phones just lit up saying, driver is 2 minutes away. But obviously, Dave only has one car. This is how you get complete matching chaos and instantly ruin trust in your platform.
Which takes us right into Section 3, the heroic fix, atomic locks. To absolutely prevent this double booking disaster, the system needs strong consistency. We need a bulletproof way to guarantee that when a driver is claimed, they are locked in instantly, and nobody else can touch them.
Uber solves this by using something called compare and swap, or CAS, SQL transactions down at the storage layer, and watch multi-exec commands up in the Redis in-memory layer. Okay, I know that sounds like a bunch of heavy tech jargon, but just think of it like a physical key to a single lockbox. If two people reach for that box at the exact same time, only the very first person to actually turn their key gets what's inside. The lock physically jams for the second person. It's an atomic operation, meaning it happens completely all at once, or it doesn't happen at all. Let's move to the exact sequential flow and see how this builds in Redis. First up, the watch command. The server issues this to basically stare at the driver's state and make sure no one else touches it. Second, multi. This initiates the atomic transaction block. And third, exc. Fires to instantly flip that driver's state from idle to reserved. If another server even breathed on that driver's state in the tiny window between the watch and the exc, the entire transaction just instantly fails. Poof, no lock is granted.
And honestly, this beautifully illustrates how gracefully a well-designed system handles failure. First right wins, right? The lock is committed, the state transitions, and the driver is physically assigned to writer A. But what about writer B? Their write fails. But instead of the app crashing or throwing a messy error screen, the system just rejects that second request in a fraction of a millisecond and silently cascades down its candidate list to immediately offer writer B the next best available driver in that S2 cell. Writer B literally never even knows they lost a race for that first driver.
Section 4, the invisible triumph. At the end of the day, the ultimate goal of all this intense, frantic engineering is that you, standing there in the rain, experience absolutely none of it. We talked about millions of writes, S2 geometry, Redis clusters, and atomic locks. But the real victory? The real victory is the completely seamless experience.
So here's the absolute crucial takeaway for us. A phenomenal distributed system is entirely defined by its invisible handoffs. You just tap a button. Meanwhile, the system performs sub-millisecond searches across a mathematically folded geographic map. It batches offers over a few seconds to optimize the entire city's flow. It deploys atomic locks to guarantee you aren't fighting another human for a car. And it relies on eventual consistency to keep that massive data fire hose from just crushing their servers. All of this is happening concurrently, self-healing instantly if a single network ping drops.
As one of the core engineering philosophies from our source material so perfectly puts it, build for the failure path first. The happy path takes care of itself. This dispatch system isn't amazing just because it works perfectly when you have 5 bars of 5G and everyone is standing still. No, it's amazing because it assumes connections will drop, it assumes GPS coordinates will drift, and it assumes thousands of riders will request the exact same drivers simultaneously, and it handles every single one of those failures without you ever noticing.
The true benchmark for a production-grade system isn't whether it works when things go right. It's whether the users never notice when things go wrong. So the next time you're out, you're tired, and you tap Confirm Ride, take a second to look at that 3-second loading spinner. What invisible miracles are happening right there in your pocket to pull a massive metal car out of the physical world and route it right to your feet? Thank you so much for joining me on this explainer. I really hope this gave you a whole new appreciation for the absolute mountain of engineering hiding just behind your screen.